Let's draw the structure of xenon tetrafluoride. So that is the name of this molecule. So xenon is a noble gas, and noble gases are happy at 8. Carbon is happy at 4, nitrogen 5, oxygen 6, halogen 7. All the noble gases are going to be happy at 8. Fluorine as a halogen is happy at 7, but we got 4 of those, so we've got 28 electrons, so 8 plus 28. Our goal is to get 36 valence electrons around the xenon tetrafluoride molecule. So let's make xenon our central atom, because we don't know which of the 4 fluorines do you want as central. So xenon will make the perfect candidate as a central atom, and then we're going to bind to it 4 fluorines. 1, 2, 3, 4. So remember, this is the one-dimensional structure on a piece of paper. What it looks like in 3-dimensional space is something we don't know yet. So 36, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32, let's put 33 and 34 and 35 and 36 back on the central atom. So any leftover electrons, 33, 34, 35, 36, those electrons are going to go back to the central atom, and that will be the correct structure of xenon tetrafluoride. Everything is accounted for in terms of our 36 valence outer electrons. And let's look at the formal charge considerations for this xenon atom, the central atom. So formal charge is most important. So 1, 2, 3, 4, 5, 6, 7, 8. Xenon is happy at 8. 8 minus 8 is 0. So that's a good thing. I'm very happy I put those red electrons back on the xenon because it minimizes my formal charge. How about the octet rule for xenon? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my octet rule is 12, but that's okay. That's okay because I can have what's called an expanded octet. So the fact that I got my formal charge 0 is much, much better. Remember, you don't see any charge here. In fact, you don't see the charge on the water. You don't see any charge on the XeF4 xenon tetrafluoride. And this way, to get the expanded octet, I removed a charge because there is no charge on this molecule, right? So the expanded octet is totally fine. Let's look at the fluorine. Okay, fluorine here. Halogens generally, especially if they're outer substituents, like to be single bonded. And let's look here. Formal charge. Okay, so 1, 2, 3, 4, 5, 6, 7. Fluorine is happy at 7. 7 minus 7 is 0. Let's look at the octet rule for the fluorine. Okay, realizing that this fluorine, this fluorine, this fluorine, and this fluorine are all the same. They're both single bond to the xenon. So the octet rule, 1, 2, 3, 4, 5, 6, 7, 8. So here you count everything as 1 for the octet rule. And this satisfies the octet rule. So this would be the correct one-dimensional structure of xenon tetrafluoride. It has, let's see here, 4 bonds. Look at the xenon now, the central atom, 4 bonds. Bond 1, bond 2, bond 3, bond 4. It has 4 bonds. They just all happen to be single. 4 bonds, and then I have 2 lone pairs. 4 bonds, 2 lone pairs. So how will I get to 4 bonds and 2 lone pairs? I'm going to have to pick some of the d orbitals, right? Because 4 plus 2 is 6. So 1 from the s. P has 3, so 3 plus 1 is 4, and then I'm going to pick 2 from the d orbital. Remember, d has 5 slots, so 2 plus 3 is 5, 5 plus 1 is 6. These are the 6 orbitals that I will utilize to get 4 bonds and 2 lone pairs, total of 6. This is an sp3d2 hybridized Z. Also, this will be a nonpolar molecule. So generally I like to draw it in 3D, but we can draw it one-dimensionally. This fluorine is going to pull up and make it partial negative, canceling out by the pull down of the bottom fluorine. The one on the right is pulling in its own direction. You see fluorine is very electronegative. And the fluorine here on the left-hand side cancels out the pull from the right-hand side. So this is a nonpolar molecule. 4 bonds and 2 lone pairs. So we're going to use table 10.2 or whatever equivalent table you have from your book or the internet. So 4 bonds and 2 lone pairs. So number of bonding pairs, let's go all the way down to 4. And number of lone pairs, let's go all the way down to 2. You'll notice it's at the bottom of the table here. So 4 bonds, 2 lone pairs. The molecular geometry is square planar. So this is a square planar molecule. So the 2 lone pairs actually force this molecule into a nice perfect square. So let's see if we can draw that 3-dimensionally. There's many ways to draw it. I can draw it where it's perfectly flat. Let me draw it a little bit more creatively. Okay, so I'll have the 2 fluorines come out towards you guys. So this is called a dash. And then I'll have the other 2 fluorines come back away from you guys and me. We'll call that bond dash. So we have the wedge, and then we have the dash. So the bond's coming towards you. I think I misspoke earlier. The bond's coming towards you, this little black one, that's called the wedge. The bond's going away from you, that bond is called the dash. Again, we're just trying to get this 3 dimensions in 1-dimensional piece of paper. And then let's draw the lone pair of electrons, lone pair 1 and lone pair 2. Let's have it going above on the plane of the piece of paper and below on the plane of the piece of paper. So the 2 lone pairs of electrons distort the molecule, but they distort it so that it becomes a square. Okay, another way I could draw this, you can see this molecule here, those 2 fluorines coming out towards you and the 2 fluorines coming back away from you. If I flip it 90 degrees, what happens is that everything is now on the plane of the piece of paper with regards to the 4 fluorine substituents. Okay, imagine taking this fluorines coming out towards you and flipping it. Now it's back on the plane. This one in the back is also on the plane, and this pair of electrons is now coming towards you guys, away from, towards the paper coming up, and this pair of electrons is going behind. So basically there's many ways to draw using these dash and wedge types of bonds. Okay, and whatever it is, the molecular geometry is square planar, and it's a nonpolar molecule. You can also see the nonpolarity here. You see this fluorine is pulling, being canceled out by that fluorine pull. This fluorine pulling is being canceled out by that fluorine pulling. This lone pair of electrons pulling up is going to be canceled out by that lone pair of electrons pulling down. So yes, this is a nonpolar molecule. Square planar is the molecular geometry that we get consulting the table. It's an sp3d2 hybridized xenon. That's how we're able to get 6 bonds. 4 of them bonded to fluorine. 2 of them are lone pairs.